So Newton's method. If you're watching my previous video, right? Little plug for my previous video, section 4.7. If you're watching the previous video, then we learned that Newton's method was a way to solve this equation. F of x equals 0. Now, a lot of times you can't solve those things directly, so you have to solve them numerically. You have to do a numerical method. And that's what Newton's method is. It's a numerical method. Now let me pass out some handouts for Newton's method. Try and make sure that it gets through to everybody, please. But Newton's method is also going to be what's called an iterative method. That is, what you're going to do is you're going to find a guess and then improve that guess and keep on using new guesses to make improvements and refinements to another one. So let me kind of give you a graphical idea of why or what we're doing with Newton's method. So we're trying to solve for where a function crosses the x-axis, that is, equals 0. So here's your f of x, y equals f of x. And what Newton realized is if you had a guess as to where a function was equal to 0, then you can improve upon that guess by using the tangent line. You could find the equation of the tangent line and use that equation to get a better guess. Call it x1. So you start out with your initial guess, x sub 0, and you get another guess, call it x sub 1. And then you take that guess and you put it back into Newton's method and get another improved guess. And you keep on doing that until you don't see much difference between successive guesses, and at that point you're like, okay, I've got enough accuracy here. So I'm not going to actually derive Newton's method for you here today. It's not that hard. All you have to do is fit the equation of a line. Actually, it's y minus f of x equals the slope of the tangent line, which would be f prime of f of x times x minus x sub 0. And then what you want is you want to know where this line equals 0. So the y-coordinate is 0. And when you solve here, what you end up with is Newton's method. I'll call it x sub n. Let's call it x sub 1. Let's call it x sub 1. Keep it simple there. So x of 1, that's our new guess, equals our old guess minus our function at the old guess divided by the derivative of the old guess. So that's how you take your old guess and update it to get a new guess. So here's your old guess, and you subtract off this little bit of a correction factor to get an improved guess. And once you have that one, you feed it back into this loop and start that process all over again. Okay, so we'll start with problem number 14 here. Problem 14 looks like this. We've got f of x is negative 2x to the 5th plus 9x to the 4th minus 7x cubed minus 11x. And we want to know where this crosses the x-axis. Now, there could be up to 5 solutions to this. One of them would be certainly x equals 0. But the solution we're looking for, this is given by the book, is in the interval 3 to 4. So, okay. In order to set up Newton's method, I'm going to need a couple things. I'm going to need an initial guess, and I'm also going to need the derivative. So let's do the derivative first. F prime of x, well, negative 10x to the 4th plus 36x cubed minus 21x squared minus 11. Okay. Now we're not actually going to do this by hand. There's certain people that might want to do it by hand. I don't want to be one of them. All right, so how do we do this with technology, with a calculator? Well, take out your calculators. And for this one, if you've got a Texas Instrument calculator, I recommend it. If not, come borrow one. You can do these things on the Inspire. I'm just not exactly sure what the commands would be. There we go. Welcome. Welcome. Good question. For this one, it doesn't matter if you're in radians or degrees because we're not dealing with any trigonometric functions, so we're okay there. But in general, as a general rule, what do you think you want to be in? Radians. Yeah, calculus is done in radians. Generally, you probably want to stay in radians. So let's put in both of our functions into y1 and y2. So the first one, that's our f of x, negative 2, x raised to the fifth. Press the right arrow to exit the exponent, plus 9, x to the fourth. Again, right arrow, minus 7, x cubed, minus 11x. So that's our function. Let's put in the derivative as well. So it's going to be negative 10 x to the fourth plus 36 x cubed minus 21 x squared minus 11. You know what? I'm missing an x on top. Yep. Thank you. That would have messed things up big time. Now let's do ourselves a little bit of a favor here. Go over up to here in y2 and shut off that equation. So just put your cursor on this and press enter, and it shuts off that equation because I don't want to graph that equation. All I'm interested in is the function. So let's graph the function. And they actually told us the interval, right? The interval is 3 to 4. So I'll put 3 to 4 here and then do zoom 0. That'll give me a nice graph, already fit the scale. And you can see that the graph, or function, crosses the x-axis somewhere around here. We can actually use a graphing calculator to figure that out, but the idea is to use Newton's method. So everyone got that graph? Got your function in correctly? All right. Let's start with Newton's method. Now, I'm going to give a kind of an inaccurate guess, an initial guess. Let's say that it's about 3.5. I mean, I could do better than that, maybe 3.2, 3.25, but we'll just keep it simple. So our initial guess, x sub 0, is 3.5. So let's store it. Let's store our initial guess. So that's this stuff right here. So here I stored 0.5. Now we're going to store 3.5. So clear out of there and do 3.5, the store key, and store that in X. Store key. It's right above the on button on the left-hand side. Stow it. All right. Store. Ooh, ah. Wait a minute. I wasn't ready for that one. Ready all together? Ooh, ah. Cool. Thank you. Ooh, ah. So we can store that value, and just for future reference. Now you can use it for anything. You can type in x squared minus 1 divided by x, and hey, that value is there. And if you type in x again, x is still there. And if you're worried about it, you can store 0 on it. It's nothing. Don't worry about it. It's not going to affect your graphs. You can take 0 and store over x, but the value of x there doesn't affect anything. So you don't have to worry about unstoring it. All right, so we got 3.5, and we store that in x. And now we want to set up Newton's method. And here's the process that you do to set up Newton's method. And the way I've notated down here Here's your current guess. To get the next guess, you want to do this. And here's all the keys that you have to press in order to follow along Newton's method. So see if you can't press these keys in exactly the order that I have, and that should give you this part right here, which is going to be your guess minus the function at your guess divided by the derivative of the guess, and then it's going to store it back in x. So you're going to update your guess is what it's going to do, and it's going to continually update it. So try and follow along. So the vars key is right here. If you're looking for vars, you're like, where's the vars? Then you go to the right. Divided by, and then kind of repeat that a little bit. Store back in x. I told you to borrow one of mine. we can go back and look at the tape. I did say that. All right. So this is an improved guess, right? So this is your initial guess. This is an improved guess as to where the root is. Now you're going to like this part. This is the cool part. Is everyone able to get this far? Got this as your initial guess? No? Yes? Some struggle? You got that far? You got that far? Noel, are you doing okay on that? Is that it? Do you need some help? Bring your calculator up here if you need some help. No? You're good? Sky? Okay. All right. Let's see. Oh, you've got parentheses around this stuff here in the bottom. So yeah, your derivative isn't programmed in correctly. So let's get rid of that and this. So there. Try it now. Let's see. 11x. Let me just double check here. So y equals right there, so 36. All right, so there. Oh, boy, that's strange. I'm not sure what's going wrong there. 3.5. There's got to be a subtle mistake in something. Oh, that's your 7x squared should be 7x cubed. There you go. Okay. All right. So everyone's able to get this, right? Everyone with the TI-84. Okay. Now the cool thing is that we need to do this again, right? So wow. Anita's like, oh, are you kidding me, man? We got to do this again. But watch this. To do this again, just press the Enter key. I press the Enter key again. All right, ready? Go. Ooh. There we go. All right. So when you keep on pressing the Enter key, and it updates these things automatically. And look what happens to your root here, or your estimate of the root. You know, it gets refined, it gets refined, and it gets refined. Now the difference between these successive terms is getting smaller and smaller, right? You got the 2.7 locked in, then the 2.74, 2.744. Wow, look at that. There's hardly any difference here. And at that point, you can say, okay, that's it. You know, I finally got something close enough. But you decide the tolerance that you need. How far do you need to keep going? But, you know, it's pretty cool. I mean, look, after 4 or 5 iterations, you're done. You've got plenty of accuracy for this particular problem. Yeah, you know, I don't envy anyone doing this by hand. I really don't. I mean, you could, I suppose. Yeah. Nobody mind. Now, I'll tell you what. So, you know, even though some people might think differently, this course is about calculus. It's not necessarily about the technology. And what I'll do for you is I'll make Newton's method on the test a little bit easier for you. Up here in the upper right-hand corner near parent, put like is, awesome, or great, or your favorite superlative, and then I'll let you use this sheet during the test. How about that, okay? Ooh, ah. All right. So, but don't put anything else on it. I don't want derivative formulas on the back or anything like that. All right. Try to keep it pretty clean other than that, but then you can use this on the test. And the idea is that I don't want you to remember, you know, all the little nuances of how to program a graphing calculator. I want you to know the calculus. And some of the calculus that you're going to need is to find the derivative. So how are we looking on that one? Okay? First one pretty good? So our answer, kind of x sub final, our final answer was 3.2744. You know, you go as many digits as I asked for, 7, 2, 6, etc. You know, and I'll tell you, answer to the nearest 10,000. I think the book asks for things down to 6 or 8 decimal places. So I'm like, okay, you got more free time than I do. All right, I don't want to grade that many. Okay, let's go down to problem number 18. Let's see. Well, you're going to use it when you want to try and solve these types of equations. F of x equals 0. Some function equals 0. And it's not something that you can easily factor or solve in any other way. That's when you're kind of forced into this kind of numerical method. So, for instance, problem number 18 asks us to solve x squared minus x equal to the square root of x plus 1. So, wait a minute. That's not exactly what Newton's method is about, right? Well, tell you what. Let's look at this graphically first. And I'm going to look at it graphically first by looking at two different graphs. Y equals the square root of x plus 1, and y equals x squared minus x. And what we're looking for there is where those graphs intersect. So here you go. And it looks like there's two places of intersection, right? And Desmos is really user-friendly. It already kind of gives you those places. But, you know, that's not what Newton's method is for, is it? Newton's method is for finding where something crosses the x-axis, where it's equal to 0. So let's take a look back at our function, or our problem. I'm going to do the following trick. I'm going to take and I'll move this to the right-hand side and get 0 equals x squared minus x minus the square root of x plus 1. And I'm going to call this f of x. That's my function. And you see the little trick here? Where f of x equals 0, then move that to the other side, then these two things have to equal. So I've created a function whose roots, that is its x-intercepts, are where these two things are equal. I'll pause for a second, because that's a trick that you need to see, is how to rewrite these things and manipulate it so that you can use Newton's method. So it started out on the left-hand side. I moved it over to the right-hand side, and it changed signs. And on the left-hand side, you're just left with a 0. So that's what's going on there. And this is something for which I can use Newton's method, because I'm trying to find where a function equals 0. So how are we going to do this for Newton's method? Well, there's probably a couple things I'm going to need first, right? What's one thing I'm going to need first? The initial guess and the derivative, right? So let's start by finding the derivative here. So f prime of x bless you. Now, it might be helpful in finding the derivative to kind of rewrite that square root term. How could I rewrite that square root term that might be helpful? X plus 1 to the 1/2. Good. So Hope, what would the derivative look like, please? X plus 1 to the negative 1/2. Thank you. Good. So let's plug in f and f prime into our calculators. So let's clear this out. What's that? No, we weren't given an interval on this one. So you're going to have to look at the graphs of the functions, and we can look back at our decimals page in a minute, or you can actually just graph it on your graphing calculator. That doesn't hurt either. So let's see here. We got x squared minus x minus the square root of x plus 1 and 2x minus 1 minus 0.5 times square root of x plus 1. Well, actually, no, not the square root. It's x plus 1 to the negative 0.5. Let's look back at our graphs. Let's take it easy on ourselves. You know, a modestly accurate initial guess would be, say, 2. 2's not bad. Newton's method converges really fast, so you don't have to worry about getting obsessively close. So we'll let 2 be our initial guess. So let's go through that process again. Exit this. Take 2 and store it in x, like that. And then you can work your way through those sequence of commands that are down here at the bottom of this page, or the shortcut, Sarah. This is kind of cool. If you hit the second key, then the enter key, it brings up your previous calculations. And if I go do that twice, then guess what? I still have Newton's method there, right? Oh, all of a sudden people are like, oh, that was cool. If you hit the second key, then the enter key, it brings up your old calculations. So if you do that like twice, you'll scroll back to where you're already punched in Newton's method once. So it's just a faster way of pulling up this calculation. That's our initial guess. Here's your refined guess. Refine that. Refine that. And look, after 3 guesses, we've got like 5 digits of accuracy. Yeah, we've got actually more than that. We've got like 10 digits of accuracy after 3 guesses or 3 iterations with Newton's method. That's pretty impressive. So, oh, why did I make 2 my guess? Well, I looked at the graph, and you know, the graph on Desmos shows me that, okay, near 2 is where these 2 lines cross each other. So that's why it's my initial guess. Now, how about over here? A good initial guess would be negative 1/2. So after we finish with this one, so let me come back here. We got one solution is x is 1.897, 179, etc. That's one possibility. Or there's another possibility near negative 1/2. How do you think I'd find that one? Yeah, plug in x equal negative 1/2. That's our new initial guess. So we're going to go after the other one. We need a point that's closer to that. So take negative 0.5 and store it in x, and then type in all those things again, or be really clever, hit the second key, then the enter key, do that twice, and that should pull up your previous calculations. Have I not shown you that trick before? Okay. So, again, look, after 3 iterations, wow. I don't think that'll change if I hit enter again. Nope. Same. So, pretty nice. X equals negative 0.484, 028, dot, 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 dot. Yeah, it's just changing at digits that are well beyond what we can see in our registers. Jeanette? You got to be careful about what you graph, because if you you don't want to look at the graph of the derivative at all ever with Newton's method. Now, in this particular case, if you are going to use Newton's method and you want an initial guess, what you could do is this. Let's shut off the graph of the derivative. We don't ever want to see that with Newton's method. It's just going to confuse you. Don't look at the graph of the derivative. Let me give a window of, say, let's go negative 3 to 3 work? Yeah, negative 3 to 3 will work. And I'm just going to make some guesses here. Negative 6 to 6. And hit the graph key. Now what we're looking for is where the graph crosses the x-axis. So an initial guess would be here at near negative 1/2, and another initial guess would be like 2. So those would be good initial guesses. So that's what you might have to do as you run through Newton's method. So, yeah. All right, good question. Thank you. Appreciate that. No, not there yet. Not there yet. So let's recall that in section 4.7, we had a problem for which we had to find where f of x was equal to 0. So from 4.7, number 24, we solved, or at least I said we could solve this equation in the last section. F of x, I think this was actually the derivative, so maybe I should call it f prime of x, but whatever. 2 times x minus 4 plus 2 times sine of x minus 2 times cosine of x. And I want to know, where does this equal 0? Where does that cross the x-axis? So this one I've got set up with Desmos. You can graph that function, and you see a couple places. If I'm just interested in this first one, that's fine. Now, what I also did is I set up Newton's method right here. And I'm not going to graph it. You don't want to see it graphed. But I called it capital N of x. So I took a first guess of 0.5. Now, that's a really crappy guess as to where this graph crosses the x-axis, isn't it? Not very good at all. But I plugged it into Newton's method, and what did I get? I got 2.43. So I take 2.43 and I plug it back into Newton's method, and I get this, 2.65. So I plug that in, 2.654 into Newton's method, and I get this. And guess what? After a couple iterations, even with a crappy guess, I still get, all the digits that I could care for. Brandon?
So whatever point that you guess on the x-axis is just going to go towards the point that's
Usually. Yeah, if I started with 4, that's a good question. If I started with, let's see. Let's start with, say, 4.2. Let's do 4.2. And then I'm getting closer to this one. So now I got 5.47. Let's put that in here next. 5.47. I get 4.67. Okay. Let's keep going. 4.676. And this one's bouncing around a lot. But see, there are problems that can occur with Newton's method. And that's one of the things that I want to get to in just a little bit. We'll do problem number 31. So 5.069. Okay, and finally I'm starting to get things settling down. You can see that we got the first couple digits, and then I can keep going from here. So 5.0957. Okay, and so it's starting to settle down, but it's a little bit slower here. And I can't, without doing a little extra analysis, I can't really figure out why it would be a little slower here. But there is a possibility that I'll discuss in a little bit when we do problem 32. So, great question. Thank you. But I hope you can see what's going on here. You keep on feeding this back into itself. You do one, and then it feeds back into the other. That's how Newton's method works. It's an iterative method. People who study that stuff in college work on a subject called numerical analysis. And basically, it's how to do math on a computer. That's the way I see it. Because at some point, you have to make your calculators do these things. All right. Just a couple more problems to finish this section out. Problem 16. I'm going to let you try one all by your little lonesome. So, actually, you know what? We'll figure out what f of x is. I'll let you figure out what f of x is. We want to solve... well, it's to be determined by you. We want to figure out where 3 times sine of x equals x, and we want the positive root. And so, yeah, you're going to need to create your own function in this, and you're going to need to come up with an initial guess. So, I'll let you work on that. We've done one like this. Let me kind of walk around a little bit, help out a little bit. Help each other out, too. Okay, so we've got a couple ways we can solve this, but one way or another, we've got to move one of these terms to the other side. So I'm going to do it this way. 3 sine of x minus x equals 0. So that's the function that we want to use. 3 sine of x minus x. So that's our function. F prime of x would then be 3 cosine of x minus 1. Let's enter both of those. So, let's see. By the way, if you ever get an error, you know, your calculator doesn't like something, telling you something about dimensions, check and see if your plot accidentally got turned on. Just shut it off, go up there, press enter, and then come back down. But you shouldn't have these plots turned on until you're taking statistics. So, 3 sine of x. You need to finish that with a right parenthesis. So right parenthesis, and then minus x. And then the derivative, 3 cosine of x. Again, a right parenthesis, minus 1. And I'm going to shut off that graph right there. I don't want to see the graph of the derivative. Now, another important thing. This calculator is in degrees, but calculus is done in radians. So I got to go change the mode from degrees to radians. Let's see, a good window, well, that should be decent enough, -3 to 3. Let's see if we can get a view of our graph. Phew, just barely. All right, cool. What we're looking for is the positive root here. So that's going to be this one. So a decent initial guess would be 2. You can do 2.5 if you want. I'm just going to keep it simple at 2. So clear out of here. 2, store an x. And then recall my previous functions and let the calculator do its magic. Nice. So after 4 iterations, you get something about like that. I don't think we're going to get much better than that. So, cool. Tal? You should hit enter until you see that these don't change anymore. So, I mean, from here to here, there was only a change in, like, you know, the last decimal place. Here to here, there wasn't a change at all. So once you see that there's no change in your function or the values, that's good enough. Yeah, and you just press enter a few times. I mean, chances are you're not going to have to press enter that many times. So x is 2.2788, like that. How are we looking on that one? Pretty good? Everyone's going to ace Newton's method? All right. There's a little bit more to Newton's method, and we can see that with problem number 31. So if it's okay with you, I'm going to do one of your homework problems. Is that okay? Are you sure? I don't want anyone flaming me on Rate My Professor. Guy always did my homework problems for me. It was such a drag. Okay. So 31 says, explain why Newton's method doesn't work for f of x is x cubed minus 3x plus 6. We want to find the root of this if our initial approximation x sub 0 equals 1. And that's what I'm going to use for my initial approximation is x sub 0. So, okay. Well, let's take a look here. What would f prime of x be? All right, 3x squared minus 3. Okay, so we're going to set it up. X sub n equals x sub n minus 1 minus f of x sub n minus 1 over f prime of x sub n. Basically, our initial guess is going to look like, or to get our next value, called x sub 1, is going to equal x sub 0 minus f of x sub 0 over f prime of x sub 0. For us, it looks like 1 minus, well, it'll be 1 cubed minus 3 times 1 plus 6 over 3 times 1 squared minus 3. Ooh, this would make somebody happy. Do it by hand. But there's a reason I'm doing it by hand. If you did this on your graphing calculator, it would blow up. Yeah. Not exactly, but it might give you an error. It's going to give you an error. Can anyone see why I would get an error here? Bless you. Yes. Yeah. The denominator is equal to 0. So, wow, at that point, you're undefined. So, where Newton's method could break down is if at some point in the iteration, the derivative is 0, or very close to 0. That's going to be a big problem for Newton's method. So let's keep track of a couple of these things here. Places where Newton's method might not work. So things that can go wrong with Newton's method. The first one is that the derivative is equal to 0 or very near 0 at some point in the iteration. F prime of x equals 0 or very close to 0 at some point in the process or iteration. That's a problem. You can't divide by 0. Your calculator doesn't like that. Literally speaking, there was a aircraft carrier, a nuclear-powered aircraft carrier that had a computer program that branched to a division by 0, and it shut down the system, and the nuclear aircraft carrier had to get towed into port, and it was there for 3 days before they could restart it, all because they divided by 0 at some point. Whoops. Yeah, you want to stay away from division by 0. Bad things happen. It does give you an error. The other thing that can go wrong is if your initial guess is too far away, it might not converge. The initial guess is too far away. And again, you're going to have problems with some of them. Sometimes Newton's method converges just about no matter what. But other times, it's pretty sensitive. It depends on the function and the derivative, how they interact with each other. There's nothing that I want to try and say in terms of something general. But, if your initial guess isn't that good, it might not converge to what you think. So that could be another problem. And we'll just keep it here. Just realize that there are places and reasons that Newton's method might break down. And that's something I might ask you on for the exam. Yeah, so, at 1, this has, the derivative has a root at 1. So it's going to equal 0 at 1. So when you get close to 1, then things are going to break down, because you're going to divide it by something which is closer and closer to 0. Yeah. Okay, for homework, try 7 through 19. So 7 to 19. And let me give you a hint for problem number 11. Use f of x equals x to the 4th minus 75. Now, why is that? Well, the problem in number 11 is to find an approximation to the 4th root of 75. Well, to create a function that says, okay, I'll do x minus 4th root of 75, almost seems circular. The point here is that you're trying to estimate this with Newton's method, not just calculate it directly off your calculator, which is what you do if you just move this to the other side. But if I raise both sides to the fourth power, then I get x to the fourth equals 75. And really, Newton's method gives you a way to calculate things like this. In fact, the early Babylonians used to use essentially Newton's method, and when you apply it this way, you can actually figure out square roots, the square root of a number, by repeatedly applying Newton's method. So, pretty clever of them. Really clever, in fact. So, okay. Cool. Enjoy Newton's method.